So in this lesson I'm going to look at finding the orthocenter of a triangle. An orthocenter of a triangle is a point where the altitudes of a triangle intersect. So let me just move this set square. I've put in two set squares here to help me find altitudes. I've put them in at the right angle already because it's kind of awkward moving set squares around on my interactive board, so I have them kind of prepared, ready to go. So I want to find the orthocenter of this triangle with vertices at -8, 6, 0, -10, and 6, 8. That's my goal. So what is an orthocenter? Well, it's the point of intersection of the three altitudes. So what's an altitude? When an altitude goes from a vertex to the side opposite, but perpendicular to the side opposite. So from A, perpendicular to little a. From B, perpendicular to little b. From C, perpendicular to little c. That's how we draw an altitude. So to draw an altitude, really, I suppose I need a set square to find my right angle. And I just kind of work it around in such a way that it's passing through the vertex and perpendicular to the side opposite it. Okay, so that's really what I'm trying to do. Once I have that and I'm happy with it, then I can put in my my altitude. So connecting that point there along here, perpendicular to the side opposite. Remember, the set square is giving me the perpendicular. So that's one altitude. I use my other set square to construct the other altitude. And again, I have this kind of set up already, ready to go. And there'll be a bit of, my board is quite sensitive, so any kind of movement knocks it off a little bit. So I can put in a second altitude up here from vertex B to side little b, and we have a second altitude. So we've got a second altitude. The third altitude is also bound to go in there, and you could probably figure out what that is already. We'll look at solving that in a moment using Cartesian formulas and stuff like that. Let me look at one GeoGebra file here just to talk a little bit about altitude. So on GeoGebra, to construct an altitude, I want to go to my perpendicular line menu. I'm going to put in a perpendicular line, and I want it to go through this point A, and I want it to go perpendicular to side C, or sorry, side little a, I should say, from A, perpendicular to little a, and then from C, perpendicular to little c, and you can see there's that point in there is going to be my orthocenter. GeoGebra is telling me already it's -2, 4. I can put in my orthocenter. I can put in my third kind of perpendicular from vertex B, perpendicular to side little b. Let me try that again. That didn't work. Put in my third perpendicular line from vertex B to side little b, and you can see that passes through there, that point there where those lines intersect. That's called the orthocenter. The altitudes, well, the altitudes are actually line segments, so they should stop here. The altitude here should stop there, and should stop there, and should stop there. So actually, if I put in the altitudes, I'm talking about line segments here, from here A to that point G, from E to that point C, from capital B to that point F. I'm going to get rid of my lines. And that's really, those are my altitudes in there because they give me my heights. Generally, the letter we use for altitude is H. GeoGebra hasn't done that. And we usually use H because the altitude gives me the height. If I stood this triangle on its base A, well, the height would be this altitude here. The altitude that goes to vertex capital A. One thing I should mention, if we have an obtuse triangle, and I want to construct an altitude. Do that again. An obtuse triangle. Something like so. And I want to construct an altitude in here. Suppose I want to find the orthocenter of that. Well, if I want to construct the altitude from J, where does it go to? Well, it goes perpendicular to this side, little j over here. So in order to construct that altitude, really I'd have to extend that line on beyond. So extend that line beyond, and then draw the perpendicular from there to there, from there to there, from here to here. And you can see in this case the orthocenter lies outside the triangle. Okay, so in this case the orthocenter lies at the triangle. I just want to look as I turn this obtuse triangle into an acute triangle by moving this point here. Watch what happens to the orthocenter. The orthocenter is down here at K. When I make it a right angle, the orthocenter is right on that corner, right on that right angled corner. When it's an acute triangle, the orthocenter is inside. If it's a right triangle, the orthocenter is going to be on that right angle. If it's an obtuse triangle, the orthocenter is outside. Okay, so we have to know definition of orthocenter. So how do we work this out, using Cartesian geometry? Okay, I could draw all three. I only need to draw two altitudes. So what I'm going to do is find the equation of the lines containing those altitudes, and I'm going to find the points of intersection of those lines. I'm going to be using the point slope form of the equation of a line, which says that y subtract y1 is equal to m times x subtract x1. A couple of things to note. The slopes of line segment little b. If I look at the slope of line segment little b, that's endpoints at A and C, rise over run, change in y over change in x. The change in y from 6 to 8 is an increase of 2. The change in ax from negative 8 to 6, well, that's an increase of 14. That has a slope of 7. So side little b has a slope of 7. If I look at this side little a over here, the slope of side little a is going to have a slope of rise over run, change in y from negative 10 to positive 8. That's an increase of 18. From 0 to 6, well, that's an increase of 6. So the slope of that side, little a, has a slope of 3. Okay, so if I look at if I call these, and typically we call these altitudes with the letter h, so I'm going to call this h1 and this one h2, and I'm noting that h1 is perpendicular to side little a, and h2 is perpendicular to side little b. Okay, so that's perpendicular. h2 perpendicular to little b, h1 perpendicular to little a. So I can find the slope of h1. The slope of h1, well, it's perpendicular to a, so it's going to be the negative reciprocal of the slope of a. Negative reciprocal of 3, that's negative 1/3. The slope of altitude 2, which I'm calling h2. h is the typical generally used letter for altitudes because they give me heights. If I was to place this on base b, well, h2 would be the height of the triangle. h2 is perpendicular to base b, so the slope of base b is 7. The slope of h2 is going to be negative 1/7. Sorry, I've said 7 there. That should be 1/7. 2 over 14, of course, is 1/7. 1/7. Oh, deliberate mistake, of course. Every mistake I make is deliberate, just to keep students on their toes, as you know. So slope of h2, slope of the second altitude here, is going to be the reciprocal of 1/7, which is going to be negative 7/1, or just negative 7. Okay, so we've got two altitudes, both have negative slopes. I could have used the third one either. It doesn't really matter which one I use. But I do need two altitudes in order to find the orthocenter. So to find the equation of h1, we're going to use the point slope form. h1 contains the point negative 8, 6. Y subtract y1, y subtract 6, equals m. The slope of h1 is negative 1/3. Times x subtract x1. So x subtract x1. X subtract, what's the x coordinate of a point on this line? It's negative 8, so x subtract negative 8 is going to be x plus 8. Okay, and I can rewrite that Maybe I'll rewrite it in slope-intercept form. Y minus 6 equals negative 1/3 x minus 8 over 3. Or maybe I'll put it into standard form. So I'm going to triple everything to get rid of the thirds. I'm going to add x on both sides. So I'm going to get x, tripling y will be 3y, tripling negative 6, negative 18, tripling negative 8, positive 8, and add 8 on both sides. I think I'm going to get negative 10. And that's equal to 0. So that is the equation of the first altitude. H1 has the equation when the x-coordinate is added to 3 times the y-coordinate, and then we take away 10, we should get 0. Okay, notice here x-coordinate added to 3 6's, negative 8 added to 3 18's, that's going to be positive 10, subtract 10, I get 0. I am pretty confident that that's correct. I'm going to look at the second altitude. I'm going to use the point slope form again. The second altitude here contains the point 0, negative 10. So y subtract negative 10, well that's just y plus 10, equals m times x, m times, so m of this slope of this is negative 7 times x subtract 0, which is just x. Actually 0, negative 10 is on the y-axis. It would have made more sense to use slope-intercept form here, but it doesn't matter. Y plus 10 is negative 7x. So I can solve for y here. Y is going to equal to negative 7x minus 10. Notice that's a line with a slope at negative 7 and a y-intercept at negative 10. I like that form. That's the slope of h2. I could put that into standard form by adding 7x on both sides and adding 10 on both sides equals 0. Okay, so that's my slope of h2 in there. So we have the equation of those two lines. So h2 is 7 times the x-coordinate plus the y-coordinate plus 10 should equal to 0. 7 times 0 plus negative 10 plus 10 does equal to 0. I'm pretty confident that's right. I'm actually preferring at the moment for my next challenge is to find this point of intersection. I'm preferring this version of this second line. So why am I preferring that? Because I have a value for y in terms of x, and I can just take that, expression for y that's in there. So I take that expression for y, negative 7x minus 10 is equal to y, and I can actually just substitute it in here in the other equation and solve for x. That will tell me my x-coordinate of this point here. And then to find the y-coordinate, well, we know the y-coordinate has to be negative 7 times the x-coordinate minus 10. Okay, so let's go through the finishing kind of stages. So let's call these equations, well, they've already got a name, h2. So we're going to take this version of h2. So we have y is equal to negative 7x, subtract 10. And I'm going to sub that into h2 here. h1, this version of h1. So therefore I'm going to get x plus 3 times the y-coordinate. Well, we're saying the y-coordinate has to be negative 7x minus 10. And then we have this subtract 10 equals 0. Subtract 10 equals 0. And it's a question now of just solving for this equation. Let me finish it off over here on the right hand side. So distributing across your bracket, remember both terms have to be multiplied by positive 3. So I'm going to get x, 3 times negative 7x, that's minus 21x, minus 30, minus 10 equals 0. And again, x subtract 21x, well that's negative 20x, minus 30 minus 10 minus 40 is equal to 0. Solving there, you'll see 20x has to equal to negative 40, which means that x must equal to negative 2. And what do we know about y? Well, we know that y is negative 7 times the x-coordinate minus 10. How do we know that? Well, because we figured it out already. Negative 7 times negative 2, and that's positive 14. Subtract 10, that's 4. Y is equal to positive 4. So my final answer here is this point has an x-coordinate negative 2 and a y-coordinate of positive 4. Okay, and that's how we find the orthocenter of a triangle. So practice those centers.